NENOMATICA, where mathematics meets YouTube excellence. Welcome to this lesson on defined and undefined algebraic expressions. Today, we'll learn how to determine when an algebraic expression is defined or undefined. An algebraic expression is considered defined when, for a specific value or set of values for its variables, all operations can be performed to obtain a real number result. On the other hand, an expression becomes undefined when, for some values of its variables, at least one operation cannot be performed within the real number system. Let's look at the main situations that can cause an algebraic expression to be undefined. First, division by zero is undefined in the real number system. Second, in the real number system, taking the square root of a negative number is undefined. Similarly, taking even roots of negative numbers is also undefined. However, odd roots of negative numbers are defined and give negative results. Finally, when the denominator of a fraction equals 0, the expression becomes undefined. Now, let's look at some examples to better understand these concepts. Our first example is the polynomial function g of x equals 2x squared plus 3x plus 1. This expression is a polynomial with no division, square roots, or other potentially problematic operations. Therefore, this expression is defined for all real values of x. Let's move on to our second example. F of x equals x plus 1 over x squared minus 1. We can factor the denominator as x squared minus 1 equals the product of x plus 1 and x minus 1. This expression will be undefined when the denominator equals 0, which happens when x equals 1 or x equals negative 1. For our third example, let's examine q of x equals the square root of x minus 3. This expression contains a square root, which is only defined for non-negative inputs. So we need x minus 3 to be greater than or equal to 0, which means x must be greater than or equal to 3. Therefore, this expression is defined only for values of x that are greater than or equal to 3. Our fourth example is p of x equals the cube root of x plus 1. Since the cube root is an odd root, it's defined for all real numbers. Even when the input is negative, we still get a valid real number result. Welcome to our math lesson on rational algebraic expressions. A rational expression is an algebraic expression that can be written as a fraction with a variable in the denominator. A rational expression is algebraic if it contains one or more variables. For an algebraic expression to be considered rational with respect to a specific variable, that variable must appear in the denominator. Let's look at our first example. The function f of x equals x plus 1 over x. This is a rational expression because the variable x appears in the denominator. Let's analyze this expression. We can see that it consists of two terms. The first term is x, and the second term is 1 over x. The second term is what makes this expression rational, since x appears in the denominator. Let's look at another example. Here we have g of x equals x plus x divided by x squared minus 1. This is also a rational expression, since x appears in the denominator. In this expression, we again have two terms, x and x divided by x squared minus 1. The second term contains x in both the numerator and denominator. The denominator x squared minus 1 can be factored as the product of x minus 1 and x plus 1. When working with rational expressions, it's important to identify domain restrictions. The value of x cannot make the denominator equal to 0, as division by 0 is undefined. For our first example, f of x equals x plus 1 over x. The domain restriction is x cannot equal 0. For our second example, g of x equals x plus x divided by x squared minus 1. The denominator equals 0 when x equals positive 1 or negative 1. Therefore, the domain restriction is x cannot equal positive 1 or negative 1. Let's visualize the graph of our first rational function to understand its behavior. Here's the graph of f of x equals x plus 1 over x. Notice that there's a vertical asymptote at x equals 0, which corresponds to our domain restriction. Rational expressions can be combined using algebraic operations like addition, subtraction, multiplication, and division. When performing these operations, you need to follow the rules for fractions, find common denominators for addition and subtraction, and multiply or divide numerators and denominators appropriately. In summary, a rational expression is an algebraic expression that contains a variable in the denominator. When working with rational expressions, remember to identify any domain restrictions by finding values that make the denominator zero. These expressions follow all the normal rules of algebra for fractions, but you must always be careful about the domain restrictions. Let's start with the definition of a rational expression. A rational expression is an algebraic expression that can be written as a fraction where both the numerator and denominator are polynomials and the denominator cannot be zero. Before we go further, let's quickly review what a polynomial is. A polynomial is an expression consisting of variables and coefficients using only addition, subtraction, multiplication, and non-negative integer exponents. For example, expressions like x squared plus 2x plus 1 or 3xy squared minus 5 are polynomials. On the other hand, expressions involving square roots, negative exponents, division, or other operations are not polynomials. For example, the square root of x, x to the power of -1, or the absolute value of x are not polynomials. Now, let's see an example of a non-rational expression. Here we have f of x, y equals x plus the square root of x plus 1 plus 2y. Is this a rational expression? Let's check. The function contains the square root of x, which is not a polynomial. Therefore, f of x, y is not a rational expression. Now, let's check some examples and classify them as rational or non-rational expressions. Let's start with some simple cases. 2/5 is rational because both numerator and denominator are constants, which are polynomials. -4 is rational because both numerator and denominator are polynomials. -b is rational because both the numerator and denominator are polynomials. 1/x is rational because both the numerator and denominator are polynomials. Let's continue with a few more examples. x/y is rational because both the numerator and denominator are polynomials. x³/1 is rational because it's just the polynomial x³. x minus 3/4 is rational because both the numerator and denominator are polynomials. 10/x plus 2 is rational because both the numerator and denominator are polynomials. Let's look at some more complex rational expressions. X plus 5 over x minus 1 is rational because both the numerator and denominator are polynomials. 3x plus square root of 7 over x squared is rational because the square root of 7 is just a constant, so the numerator is a polynomial and the denominator is also a polynomial. X squared y over the quantity x minus y squared is rational because both the numerator and denominator are polynomials. 2x minus 5 over 5x cubed minus 2x squared plus 1 is rational because both numerator and denominator are polynomials. Here are a few more examples of rational expressions. X squared minus square root of 3 times x plus 1 over 9x, y is rational because the square root of 3 is just a constant coefficient, so the numerator is a polynomial and the denominator is also a polynomial. X cubed plus 2x minus 7 is rational because it's a polynomial, which we can think of as having a denominator of 1. Now, let's look at some expressions that are not rational. The square root of x, y is not rational because it's not a quotient of polynomials. Square root of x over x plus y is not rational because the numerator square root of x is not a polynomial. The absolute value of x minus y is not rational because the absolute value function is not a polynomial. 1 over the square root of x minus 2 is not rational because the denominator square root of x minus 2 is not a polynomial. Let's summarize what we've learned about rational expressions. A rational expression is a fraction where both the numerator and denominator are polynomials, and the denominator cannot be zero. To determine if an expression is rational, check if it can be written as a polynomial divided by a polynomial. Remember that constants like the square root of 7 are just numbers, so expressions with constant coefficients are still polynomials. However, expressions with variable terms under a square root or with absolute value functions or negative exponents cannot be rational expressions unless they can be simplified into polynomial form. Understanding rational expressions is essential for algebra and calculus. These expressions follow special rules for manipulation, simplification, and operations that we'll explore in future lessons. Practice identifying rational expressions to build a solid foundation for your mathematical journey. Welcome to our math lesson on rational and irrational functions. Today, we'll learn how to identify whether a function is rational or irrational based on its form. Let's start by defining what makes a function rational. A rational function is any function that can be expressed as the quotient of two polynomial functions. In other words, a function f(x) is rational if it can be written as p(x) divided by q(x), where both p(x) and q(x) are polynomials and q(x) is not equal to 0. On the other hand, an irrational function is any function that cannot be expressed as the quotient of two polynomials. This typically happens when the function contains terms like square roots, cube roots, or other non-polynomial expressions. Now, let's look at some examples to determine whether each function is rational or irrational. Let's examine our first function. F of x equals x plus the square root of 2. To determine whether this function is rational, we need to check if it can be written as a quotient of two polynomials. Let's analyze the components. First, x is a polynomial term of degree 1. Second, square root of 2 is just a constant, but it's an irrational number. However, an irrational constant doesn't make the function irrational by our definition. Since both x and the square root of 2 are polynomial terms, their sum is also a polynomial. And any polynomial can be written as a quotient by simply putting it over 1. So f(x) equals the polynomial x plus square root of 2 all over 1. Therefore, f of x equals x plus square root of 2 is a rational function because it can be expressed as a quotient of two polynomials. Let's move on to our second example. G of x equals negative square root of x plus 2. Again, let's analyze the components. The term negative square root of x is not a polynomial term because x appears under a square root, which means it has a fractional exponent of 1/2. The constant term 2 is a polynomial. Since square root of x is not a polynomial term, the function g of x cannot be expressed as a quotient of two polynomials. Therefore, g of x equals negative square root of x plus 2 is an irrational function. Now for our third example, h of x equals 3x squared plus 2x plus square root of x. Let's analyze the components. The term 3x squared is a polynomial term of degree 2. The term 2x is a polynomial term of degree 1. The term square root of x is not a polynomial term since it has a fractional exponent. Since one of the terms in the function is not a polynomial term, the entire function h of x cannot be expressed as a quotient of two polynomials. Therefore, h of x equals 3x squared plus 2x plus square root of x is an irrational function. Finally, let's examine our fourth example. T of x equals x squared over 2 minus 2/3 x plus 1. Let's analyze the components. The term x squared over 2 is a polynomial term with a rational coefficient. The term negative 2/3 x is a polynomial term with a rational coefficient. The term 1 is a constant polynomial. Let's rewrite this by finding a common denominator to see it more clearly. T of x equals 3x squared over 6 minus 4x over 6 plus 6 over 6, which simplifies to T of x equals 3x squared minus 4x plus 6 over 6. As we can see, T of x is expressed as a quotient of two polynomials. The numerator is 3x squared minus 4x plus 6, and the denominator is 6. Therefore, T of x is a rational function. Let's summarize what we've learned about identifying rational and irrational functions. A function is rational if it can be expressed as a quotient of polynomials. If a function contains as a quotient of polynomials. If a function contains any non-polynomial term, such as a term with a square root or fractional exponent, it is irrational. Constants, even irrational ones like square root of 2, don't make a function irrational when they're not part of a variable expression. Here are our final conclusions for each of the functions we analyzed. F of x equals x plus square root of 2 is rational. G of x equals negative square root of x plus 2 is irrational. H of x equals 3x squared plus 2x plus square root of x is irrational. T of x equals x squared over 2 minus 2/3 x plus 1 is rational. Now, let's test your understanding with a quick challenge. Determine whether the function j of x equals x cubed over 5 plus pi is rational or irrational. Pause the video and try to solve this on your own before continuing. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.